Okay, so this is a video about Markov chains. So let's start. What is a Markov chain? To see what a Markov chain is, we're going to illustrate with a story. So let's meet Jim. And the thing that you need to know about Jim is that Jim is a trailblazer. Jim has a trendy new idea for his lifestyle. And this is Jim's idea. Is that every year Jim is going to move countries. The two countries that he's going to choose to move between is the United States and the UK. I guess the UK isn't a country, it's a group of countries, but whatever. So, this is how he's going to decide to move. Is that he's going to have two coins. And they're both going to be unfair coins. And it's a different coin in each country, as I've denoted here. You have this coin and you have this coin over here. So you have Jim, and he starts in the United States. And Jim, he's going to flip his coin, and if it lands on heads, then he's going to go over to the UK. And the probability that his coin lands on heads is P sub US over to UK. And then also, clearly, the probability that he would stay would be the probability that if it lands on tails. And that would clearly be P sub US to UK 1 minus P sub US to UK. Just the probability that, the probability that he doesn't go. In a similar way, if he was in the UK, then the probability that he goes, he flips his coin, if it lands on heads, the probability that he goes over to the US is P sub UK to US, and the probability he stays is 1 minus P sub UK to US. Okay, so let's just do an example adventure that Jim has. So he has his coin and he flips it, and it lands on heads. So that we know that that means that Jim is going over to the UK. And you can see here we're noting where Jim has been. So Jim's in the UK, and he has his coin, and he flips it, and it lands on tails, and that of course means that Jim stays. So that's just, you can imagine that keeps going, and we might get some sequence of where Jim has been, that he might start in the US, and then the second year he's in the UK, third year he's in the UK, fourth year he's in the US, so on and so on, and this can keep going. And there's an important property that I want you to notice about this. It's that each step in the chain is determined probabilistically. And also another key thing is that where Jim goes only depends on where Jim is and not where he's been in the past. So for example, let's assume Jim was here at like this point in the chain at whatever many years. The probability that he goes to the US or UK, it's not affected by any of this previous history. This previous history could be anything, but it would not affect, the probability of where Jim is going to go. So this, if something has these two properties, the probability one's simple, but this thing of not depending on where you've been in the past, that's essential, and this is called a Markov chain. At least that's an example of a Markov chain. So getting a little bit more like general here, and a little bit more rigorous. Like understanding everything about this definition is not essential, but putting it a little bit more clearly, it's that a Markov chain, it's a sequence of random variables, and each random variable has a particular state space, where the key property of each random variable is that depends only on the state of the random variable immediately before it. So this is, that's what this means equationally. And this thing of like only depending on, like, I said very simply, where you go only depends on where you are now. That's called the Markov property. So like just making this a little bit more, giving a little bit more detail with our particular example, like a particular realization of all the random variables of where Jim has been, like for example, a a random variable where Jim was at year 0. That, and maybe he just started in the US, but where he is at year 1 is also a random variable, and it happened to have a particular value of being in the UK, and where he is at year 2 is also a random variable. Clearly the state space, which is the value, like the actual states that can be taken for a particular random variable, are, for our case, it's either the US or the UK. And I don't want to go into that yet, but and here up at this Markov property, you can imagine, for example, this. So how you read this is that, it's the probability of this random variable being this thing given this thing over here. So like, for example, it would be like where Jim, if t was equal to 2, that would represent where he's at the second year. So let's say like this was, I don't know, let's say this was the UK or something. So x of 2 equals UK. That would mean like where he is at year 3, because t is equal to 2, so this would be 3. Where he is at year 3 only depends on where he was at year 2. So I think that should be clear. So we often represent Markov chains graphically. So this is like a, it's just, this is a graph. So, he can either be in US here, and he can either go, these are little transition arrows. He can either go to the UK, stay in the US, similarly for UK. And of course, each of these transition arrows would have its own probability of transition. So, this is saying like if he's in the US, the probability that he goes to the UK the next year is of course P sub US to UK. And then here you would just fill in all the other probabilities that we gave before. But there's another representation of Markov chains which will be essential to us, and it's representing it in the form of a matrix. So this matrix here is going to, in a very clean way, represent all the possible transitions between states. So in this upper corner here, in the way that you read this, this would be the United States row. That given you're in the United States, this records like, okay, this is the probability of staying in the United States. This one would be the probability of going from the United States to the UK. And then down here, this would be like, you can think of it as the UK row, be the probability of going from the UK to the US, because this is like the United States column. And similarly, it's just, this is the probability of going from, or the probability of staying in the UK given that you're in the UK. So of course, this, I think it's pretty clear, this matrix is called the transition matrix. It is a matrix which records all the transitions between the states. Okay. So, our story continues. So, Jim, he's a trailblazer, and naturally he has a social media, and he makes this post, and he's like, oh my gosh, look how good my life is with this crazy thing I'm doing. With moving countries every year. He makes a post about it, and everyone, basically everyone in the United States sees it, or at least is hearing about it, and every single person without exception in the United States is going to start living the Jim lifestyle. They have all collectively, they've seen the glory of Jim, and they're like, wow, we are just absolutely drawn to do what Jim is doing, and every single person is going to do it. And the people in the government are like, oh no, this is, what do we expect to happen to the population? This is craziness. Like, everyone's going to do the Jim lifestyle. And we have to figure out what's going to happen so that we can prepare. And this dude's like, what do we expect the population to do? And this dude down here, he's like, well, since, we know about the coins, we know the transition probabilities. And he's like, we can, and, he says that we can just calculate it. So that is what we're going to do. And we're going to see how this is going to work out. So we're going to represent the population of the United States by this row vector here. And the way that you read this and the way that I want you to think about this is that, you know, this column in the row represents the amount of people that are in the United States. This one represents the amount of people in the UK. So everyone starts in the United States. So, and when I say everyone, think of everyone as like that's the whole. So like everyone's the whole, so you'd represent that with the 1. And then of course no one is in the UK. So like, and then, you know, going on, if you wanted to represent half of, let's say half of the population was in the United States and half was in the UK, then this column would be 1/2, and this column would also be 1/2. So, okay, I think that's simple enough. So we want to know how the population splits, the portions of the population, how they split in each year. So we can of course do that because we have the transition matrix, and I'll denote it over here, and I've denoted, you know, each transition by a different color. So let's think about what happens in year 1. So in year 1, you know, you have everyone flips the coin, and you know, we know how the, you know, on the average how the coin's going to land. There's going to be this portion of people that it's going to land heads and they end up going to the UK. And this portion of people, it ends up that they land on tails and they end up staying in the US. And this is how this would split. So, you know, just very simply for an example, if P sub US to UK was 1/2, then half the people would have went to the US, half the people would have went to the UK. Like, okay, well, we know what's going to happen basically at year 1. So what's going to happen at year 2? Well, we just do the exact same thing again, except there's a little bit more to consider here. So of course it's the same thing. It's like, okay, now you have this amount of people in the US, and they all flip the coin, and of course they have the same probability of it landing on tails. So now you have 2, like, so this was the amount of people originally there, and then this is, you know, times the portion that are going to be in the US. But also now you have to consider that some of the people that were going to the UK are coming back to the US because they flipped the coin in the UK, and some come back to the US. So this one, so it ends up being the, you know, the total portion of all people in the United States is this whole term over here. And then it's a similar case for, you know, this side over here, where this is all the people in that end up being in the UK at the end of year 2. And you can like pause and think about this if this has not made sense. But you know, we can, you know, we do in principle have a way to keep, you know, keep going with this and keep, you know, for each year getting how the population is going to split up. But you know, this is getting kind of you can see this is going to keep getting messier and messier. So we can actually accomplish the same computation in a much cleaner way with the transition matrix and just linear algebra. And it ends up being that the way that you calculate it is basically the row vector times the transition matrix. And I guess just a note here in like Markov chain theory, you would think you would have represented the, you know, the population or whatnot, or you know, whatever your distribution is of people as a column vector, but that's not how it's done in the literature. They represent as a row vector, so that's what I'm going to follow here because I'm going to assume that people had good reason for doing that. But anyway, that's just a note I wanted to make of like, you know, this would make much more sense in my opinion if this would have been a column vector and then it would have went over here and then you would have gotten out another column vector. But anyway, this is how we're going to proceed. But anyway, like how you would calculate how people are going to split up after the first year would be where they are at year 0 times the transition matrix is going to give you year 1. And you can pause the video and think about how this matrix multiplication is carrying out and seeing that it does give you exactly what you want. And similarly for year 2, what you do is like, you know, you just do it twice because this whole term here, right here, is just this up here. It's this distribution of people that, like, you know, this percent are in the are in the US, this percent's in the UK, and you just multiply that by the transition matrix again. And if you go and work out the math, you'll see that we get exactly what we got over here. Anyway, and you can keep doing that, and like we have matrix multiplication calculators that could do this very easily for us. But anyway, this is a much cleaner way to do the computation. So we move on, and the government is like, okay, so this is crazy, man. Like, people are moving and, sloshing around between countries, and, it's a bunch of nonsense we have to put up with each year. But, will this ever stop? Will this madness ever settle down? Is it ever going to be such that, like, from one year to the next, the distribution of people is not really going to change at all? And this dude's asking, it's like, how do we find what the population stabilizes to as t approaches infinity? And here t would be the number of years. And this dude is like, hey, that's actually trivial. That's not hard to get. So this is what we want, actually. So what we propose is that, this is at, the population at any given, like, at some year where things have stabilized. You go to the next year and it's the same thing. It's like, this is year, t, and then this is year t plus 1. And when everyone flips the coin, they step a year, it actually ends up that it ends up being the same distribution of people. And it's like, well, we want to know, given this transition matrix, what is this distribution? And it's like, hey, this is just the eigenvector problem. That's all this is. This is just the eigenvector problem. We already know how to do this. Like in, in simpler, notation, it would look like that. And this pi here, this distribution such that, you go from one step to the next and the distribution ends up being the same, it's called the stationary distribution. And that's going to be a very important distribution for us. And just for this particular example, like this ends up being the stationary distribution for, for this given transition matrix, this ends up being the stationary distribution. Okay, so moving on with more theory that we need, or that we're going to cover for Markov chains, is this thing called detailed balance. I couldn't think of a way to loop this in with my story, unfortunately, but it's going to be essential for us going forward, in particular, if we want to understand Markov chain Monte Carlo sampling, is this thing about detailed balance. So we're going to go through here. So like, what is detailed balance? So generally it's a condition in which it's a condition, like, that if your distribution is in this condition, then that it's a stationary distribution. So to show it more practically, exactly what the distribution is and what this condition means, let's propose, another chain here. So this is another Markov chain. Now, instead of 2 states, it has 3 states. So if we want to continue with our analogy, let's pretend these are 3 countries. And now people can choose. It's like, okay, I'm going to choose to see if I'm going to go to, let's say you're in country A. It's like, okay, like maybe I have 2 coins now. Like maybe this is the United States, this is UK, and this is Germany. You're in the United States, and now you have 2 coins. And one of the coins that you can choose to flip is going to determine, it's the coin that you flip if you're going to go to the UK, and one of them is a coin that you're going to flip if you decide to go to Germany. So you decide which coin that you're going to flip, and you flip it and whatnot, and just kind of mapping it to the situation that we've been dealing with before. But it's these are, and these are just like arbitrary distribution, like these are just arbitrary distributions, like maybe this is like 1/2, this is 1/4, and this is 1/4, meaning like half of the people would be here, a quarter would be here, and a quarter would be here. And this is like a particular state of a Markov chain at some time. Okay, and also I'm going to denote the probabilities of transitions between states in a more compact form. The way that you read this, I mean, it's pretty simple. It's just the probability that you're in state A, that you go to state B. That's all you read this as. So this is our Markov chain. So to see this detailed balance condition, let's just focus on the relation between two of these states and like, the transitions between two of these states. And we want to ask like for a step, everyone in country A is going to like, if they want to go to this country, they're going to flip the coin. We want to ask how many people, or maybe not flip the coin, or just in general like the probability of going from A to B. So, we want to ask how many people are going to be going from A to B. So it's going to be the portion of people in A times the probability that you go from A to B. It's very simple. Similarly, if we want to ask how many people go from B to A, well, it's just like the number of people in B times the probability that you go to B to A. It's like, okay, that's pretty simple. So you think of the amount of people going from B to A and A to B. So it's that if the amount of people going from A to B and B to A is the same, and the amount of people going from A to C and C to A is the same, and the amount of people going from B to C and C to B is the same, then you could deduce that this distribution would be stationary if that happens for all time. So like I've denoted it a little bit clearer down here. This is the condition for a detailed balance. That here for this particular, if we want to look at this particular leg, it's like the amount of people going from A to B is the same as the amount of people going from B to A. And if this condition is satisfied for the relation between all the states, if this relation is satisfied for all x and y, where x and y are representing our different states, then we know the distribution is in the stationary distribution. And like this, I think this should be pretty simple to see that like if it's equal number going here to here and here to here, and then that's true for all the states, well then just like it's just an equal exchange between all the states and nothing changes. But I mean, you would, and like this condition is actually going to be essential for us, but I just want you to see here it's very simple. It's a very simple condition, and if you can find that your distribution is in detailed balance, then you know that it's like it's the stationary distribution. Yeah, and as I said, yeah, this is called detailed balance. So we move on with our story here. There is more to the story. So of course the Illuminati get wind of what's happening with Jim because they know all. So they know all, and they're like, okay, so far what we've been doing is like, given some transition matrix, we've been able to predict what the stationary distribution is going to be. So like thinking about it in terms of like, okay, the government leaders, they knew what the coins were. They knew what the coins were. And yeah, they knew what the coins were, and they wanted to predict what the stationary distribution was going to be. But they ask, okay, can we do the opposite? Can we construct, so here it's, can we construct a transition matrix to make a stationary distribution of our liking? Or put in another way, like, can we seed coins in each country such that after a long time we as the Illuminati can get, the distribution of people we want in each country? And it's like, how would you, so basically the problem statement is, given a stationary distribution you want, how can you construct a transition matrix between the states to get you to the stationary distribution of your liking? And then, like, of course, they're Illuminati. They can, of course, do that. But we're going to learn how to do that because it's important for Markov chain sampling. So, anyway, so, we start out with our sample little Markov chain here, and notice I've not specified anything about the transition probabilities. But, let's say we want this particular stationary distribution. And I guess I should have used pies here, but whatever, you know what I mean. We want this particular stationary distribution. We want to find the transition matrix that, after we've run enough steps, and like if you think of like everyone starts in this country, and they all go along, and after like, after 100 years or whatnot, you get like, you get the stationary distribution of your liking. We want to find the transition matrix to make that happen. So, we need to find the transition matrix. So I'm going to propose to us a little like scaffolding, like a little scaffolding transition matrix. And you could have like come up with this after some thought, but I need to explain what each of these elements mean. So here, x and y, so x and like, and by the way, this notation does represent a transition matrix, except it's in even more compact form that you just put in one equation, where x and y can take, the values of a, b, or c. So we have this. So for example, if x was a and y was b, you would read this up here as like, psi of a and y, a of a and y, so that like, and then whatever these numbers were, that would be the probability of going from A to B, basically, if X was A and Y was B. And then down here, this is just like another condition where, we have to make a special condition for, if X and Y are the same thing. So for example, this would like if X was A and Y was A. And all this is saying is like, hey, it's like basically the probability that you stay in the same state is just like, this is the sum of the probabilities of going to a state which is not, this is the probability of going to a state which is not x, minus 1. So, clearly this just represents the probability of staying in the same state. But really we're going to be concerned about this up here, this thing about transitioning to another state. So this is the way which you think about this. It's like the transitioning to another state is a sort of two-step process. And if we think about it in our coins example, we might have the following. If you're in country A, you have to make a choice about which coin you're going to flip, i.e. you have to propose which country you might go to. So you have two choices. You have either countries B or C. So you have to make that choice. So the probability of making the certain choice is encapsulated by this psi right here. And if you already know something about Markov chains, that's called the jump proposal. It's the proposal to go to another state. But then once you propose that you got to go to another state, you got to decide if you're actually going to go to that state, or, put in our example before, you have to decide if you're going to go to that country. And that's what this A represents here. So, moving on now, and yeah, this is, as I said, the probability to choose where you're going to go. And I guess for some, like, your jump proposal, like, jump proposals are like a kind of complex field. There's a bunch of jump proposals, but just this is not going to hurt our generality as well, but just to help us think about this, let's just say we've already chosen a jump proposal for, being in state A. Like, it's just a 50-50 chance that you go to, you propose to jump to B or C. It's just going to help free our minds a little bit. And really what we're going to be concerned about is finding this accepted, finding, basically what we're going to do is we're going to find an A. And when we find that A, it's going to be an A such that it makes our transition matrix one that gives us the stationary distribution of our liking. So two things to remember. This is the probability to propose that you're going to jump somewhere. This is the probability that you accept that jump. So we're constructing a general transition matrix like this. We want to make that transition matrix such that it's going to give us a particular stationary distribution, which is this one up here, which is already proposed. So it's given this stationary distribution, find the transition matrix. So that is our task. So, okay, how do we do that? So we already know the stationary distribution we want. That's already been given to us. And we have a transition matrix of this general form. We've not solved the particulars of this yet, but that's going to be our goal, is to solve the particulars of it to give us the particular stationary distribution we want. Well, let's ask, what condition tells us if we're in the stationary distribution? It's the detailed balance condition. So we want to find the transition matrix. We want to find the transition matrix such that the transition matrix is true for all x and y here. And remember, these mu are the stationary distribution which is given to us. And if we know our transition matrix satisfies this condition, then we know it's a transition matrix that is going to give us, the stationary distribution we want. Okay, so let's go ahead and find how we can make, this work out in general. So we start with this detailed balance condition, as I've said. And all we're going to do is we're going to focus, this is just from the, this is just from the transition matrix, that this is the probability of proposing to go from one state to another, and then this is the probability of accepting that. So we just plug that in here for our P of x and y, our transition matrix. So we plug that in here. And that's all we've done is plug this into this, and we get this one here. So then we move on, and we notice something. And we're like, hey, so I've just copied this down here. But these statements, it's also true that it's less than or equal to this over here, because a of x of y is less than 1. And you can see all I've done here is just I've taken this line here, and I've removed the a of xy, or at least made it 1. And I should get this thing here. And then I get that this is true. And you see this, of course, is less than or equal to this. I get this condition here. Okay, this should be pretty simple so far. So the next step, it's going to seem a little bit odd, but I think it'll take some thought on your own to kind of get figured out. But we're going to, so this is a less than or equals to, but let's just make it an equals to. And like the explanation for this is that this accepted step, we want to make the accepted step as high as it can possibly be. The probability that we accept a step as high as it can possibly be, because when we go over to sampling, this will make sense later, but when we go over to sampling, we want the chance that we accept a step to be as high as possible to make our sampling efficiency high, but that's why we do this equal sign here. But now we have this relation, and we just divide this thing over this side, and we get this. And it's like, hey, this is the, if you look at this, usually we just propose ourselves some sort of jump distribution, or we propose some sort of jump proposal. So, and again, this is our stationary distribution. So this is already given to us, and we kind of already know this beforehand. You already know this beforehand before you go into any any particular case. And then hey, we've calculated the chance that we go from one state to another. But if you look at this for a minute, you're going to notice that this has a chance to be more than 1. So you just if this value is more than 1, then you just it's a sure thing that you accept the step. So it's just the minimum between these two. And an exercise, so I know that was like a little bit flaky, but an exercise I want you to do is I want you to take this and put it up here. This is our detailed balance condition, and see that if we choose this as the chance to accept a certain, or the probability to accept a certain step, this does satisfy this detailed balance condition up here. And remember that if we get a transition matrix that satisfies the detailed balance condition with this stationary distribution, we've done it. And when you plug this in here and see that it's really true for this really does make the given detailed balance condition we want true, then you can deduce that when we plug this A back into our whole transition matrix, then we've done it. We have found the transition matrix which gives us the certain stationary distribution we want. And we've done it. Hooray. Amazing. That's what we wanted to do. And this is this is essentially how you do Markov chain Monte Carlo sampling, and that it's going to need more explanation. I'm going to explain how we use this to do Markov chain Monte Carlo sampling in the next video, if it's not already obvious. But yeah, I will explain that more next time.